If two waves overlap in the same medium, we say that there's wave interference. So this box here could represent a speaker, and this could be the sound wave it generates. Or it could represent a laser, and this would be the light wave it generates. Or it could be some sort of ripple tank generator, and this is the water wave it generates. Regardless, if you had a second source of a wave, and these were to overlap, you'd cause wave interference, and what that would look like would be something like this. So let's say these are speakers. I like thinking about it in terms of speakers. I think it's easy to think about. And I put this speaker right next to the first speaker, side by side. So they'd be creating sound waves in this region. And I wouldn't really have two sound waves necessarily. You can think of it as just having one total sound wave. And how would we find the size of that total sound wave? Well, if I put an axis in here, the axis will make it easier for me to think about this. I'm going to put an axis through here like this. What I can do is I can just ask myself this. I'm going to say, what was the value of the first wave? So I'm going to take that value. What was the value of the second wave? And I'm just going to add them up. To get the value of the total wave, I'd take that value of the first wave plus the value of the second wave, and well, I just get double in this case. And I can come over to here, okay, value here plus the value there. I get double that point. It's not going to be as high because they weren't as high. And then over here I got 0, and 0 is just 0, and you start to see what's happening. I can come down here, very low or very negative, and I get double that down here. And if I were to trace this out, what I'd get is one big total sound wave that would look like this. So these have been amplified. So that's one possibility. When two waves overlap, you can get this case where the peaks match the peaks and the valleys match the valleys, and you get constructive interference. So notice how each valley matches the valley, each peak matches the peak, and this is called constructive interference because these constructively combine to form one bigger wave. So this is constructive interference. So what would you hear if your ear was over here somewhere waiting to hear this sound? What you'd actually hear is a loud note. This would be much louder than it was. It'd be twice as loud, in fact, which makes sense. You've got a second speaker in here. It's twice as loud. That makes sense. What's a little bit harder to understand is you can also have something called destructive interference. What would that look like? Well, imagine you had two speakers, but they looked like this, so that the peak of the first one lined up not with the peak of the second one, but with the valley of the second one. And the valley of the first one lined up with the peak of the second one. These are out of phase, we say. Before, when they looked like this, these waves we say are in phase because they look identical. The peaks match up with the peaks, the valleys with the valleys. These are out of phase. How far out of phase are they? We say that these are 180 degrees out of phase. So these are 180 degrees out of phase. The phase refers to what point on the wave cycle is the wave at. And these two are starting completely separately, which is 180 degrees. You might think that means 360, but think about it. If you turn around 360 degrees, you're actually back to where you started. If we tried to make these 360 degrees out of phase, they'd look identical again because I've moved one so far through a cycle that it's back to where it started in the first place. So I want to move it 180 degrees out of phase. That's exactly the opposite, so that you get peak lining up with valley. Or if you like radians, this is called pi out of phase because pi and 180 are the same angle. All right, so what happens here if I take these two speakers, and if I take this second speaker and I line it up right next to the first speaker, I get something that looks more like this. Look at how weird this looks. These are completely out of phase, and what's going to happen is if I add my little axis to help me think about this, I'm not going to add an axis straight through here. Now I play the same game. What total wave do I end up with? Well, I take this value. I'm going to add up the values just the same. I take the value of the first wave plus the value of the second wave. I add those up. One's positive, one's negative. I get 0. And then over here, 0 plus 0 is 0. And then the valley of the first wave's lining up with the peak of the second wave. And if I add these 2 points up, I get 0 again. And you probably see what's going to happen. I'm just going to get a flat line. I'm going to get a flat line, and I'm going to get no wave at all. These two waves cancel, and so we call this not constructive interference, but destructive interference, because these have destructively combined to form no wave at all. And this is a little strange. How can two waves form no wave? Well, this is how you do it. And what would our ear hear? If we had our ear over in this area again, we were listening. If I just had one speaker, I'd hear a noise. If I just had the second speaker, I'd hear a noise. If I have both the first and second speaker together, I don't hear anything. It's silent, which is hard to believe, but this works. In fact, this is how noise-canceling headphones work. If you take a signal from the outside and you send in the exact same signal, but flipped, pi out of phase, or 180 degrees out of phase, it cancels it, and so you can fight noise with more noise, but exactly out of phase, and you get silence in here, or at least you can get close to it. Now you might be wondering, how do we get a speaker to go 180 degrees out of phase? Well, it's not too hard. If you look at the back of these speakers, let me make a clean view. If you look at the back of these speakers, there'll be a positive terminal and a negative terminal, or at least inside there will be. And if you can swap the positive terminal for the negative terminal and the negative terminal for the positive terminal, then when one speaker is trying to push air forward, there's a diaphragm on this speaker moving forward and backwards. When one speaker is trying to push air forward, the other speaker will be trying to pull air backwards, and the net result is that the air just doesn't move because it's got equal and opposite forces on it. And since the air just sits there, you've got no sound wave because air has to oscillate to create a sound wave, and you get destructive interference. So that's how you can create a speaker pi out of phase. Well, you might be wondering, I don't want to mess with the wires on the back of my speaker. In fact, you shouldn't, so you don't get shocked. But if I've got two speakers in phase like this, then I'm stuck. I can't get destructive interference, but yeah, you can. Even if you don't mess with the wires, and don't try this at home, you can still take this speaker. Remember before, when these were in phase, we just lined them up like that, constructive interference. But I don't have to put them side by side. I can start one speaker a little bit forward and look at what happens. We start to get waves that are out of phase. So my question is, how far forward should I move this speaker to get destructive interference? And we can just watch. So I'm just going to try this, and when we get to this point there, now we're out of phase. Now I have destructive interference. And so how far did I move my speaker forward? If we look at it, here was the front of the speaker originally, right there. Here's the front of the speaker now. If you look at this wave, how much of a wavelength have I moved forward? The amount of wavelength that you had to move forward was 1/2 of a wavelength. So if you take two speakers that are in phase and you move 1/2 of a wavelength forward, you get destructive interference again. Again, if my ear is over here, I'm not going to hear anything. Even though these two waves started off in phase, move 1/2 a wavelength forward, they line up so that it's destructive, I get no noise. But if I take this away, we go back to the beginning here, take my speaker, we start over. If you move it forward a whole wavelength, so I take this here, keep moving it, whoop, destructive interference, and now, whoa, here we go. Constructive interference again. That's a whole wavelength. So if you move it forward a whole wavelength, look at one whole wavelength forward. So the front of the speaker was here. Now the front of the speaker's here. This is an entire wavelength. I get constructive interference. Now I'm gonna hear a loud sound again. I'm gonna hear twice the noise that there would be if I just had one speaker. So the moral of this story is that even if you have speakers that are in phase, you can get constructive or destructive interference depending on the difference in length that these two waves travel. In other words, wave 2 is traveling this far to get to my ear. I'm going to call that x2. And wave 1 is traveling this far to get to my ear. I'm going to call that x1. If I took the difference between these two, I'd be finding the path length difference. The difference in path lengths that these waves are traveling, and that would be this amount. This is the difference right here. I'm going to call it delta x, because it's the magnitude of the difference between these two lengths. And we saw that if this equals lambda, it was constructive. And if it equaled a half lambda, it was destructive. But those aren't the only values. We can write down an important result here. If delta x, the path length difference was lambda, or it turns out 2 lambda will work, or 3 lambda. Imagine moving the second speaker one more whole wavelength. Well, you'd be perfectly back in phase again because you'd line back up perfectly, or 3 whole wavelengths. Again, perfectly in phase. Any integer wavelength, including 0, because 0 is just the case where the speaker was right next to speaker 1, where these two speakers were lined up right next to each other. You'll get constructive interference. The waves line up perfectly, it's going to be constructive. And we saw if delta x equals a half wavelength, it was destructive, but that's not the only case. Any odd half integer here, so I can't do 2 over 2 because that would be lambda again. I can do 3 lambda over 2, or 5 lambda over 2, or 7 lambda over 2. Any of these will give me destructive interference because they'll cause these peaks to match up with valleys. The whole thing would flatline. I'd get no sound. This is an important result. If you've got two speakers that are starting off in phase, in other words, they both start off the same way, and by that I mean one speaker sends out its wave, one speaker sends out its wave going up, the other sends out its wave going up, they're both at the same cycle. If the only difference is the path length difference, this is an important result that lets you determine whether there's constructive or destructive interference. But you might ask, hold on, what if, see, this was assuming there was no phase difference to start off with. What if you did the old switcheroo on the back of one of these speakers and you swapped the positive end for the negative end so that instead of coming out upward, the second one was coming out downward? Then what would happen? Well, you might be able to guess. Now, this result's just going to flip-flop. In other words, if I look at this case here, look at, now we start off with speakers that are out of phase to begin with. This time, if I started off with 0 path length difference, I get destructive instead of constructive. If I move this a whole wavelength forward, there's a whole wavelength, I get destructive again. 2 wavelengths forward, destructive again. 3 wavelengths forward, be destructive again. And so the integer wavelengths this time are going to give me destructive. What about the half integers? Let's see, I'll go forward a half a wavelength. Look at this, perfectly in phase. It's going to be constructive. How about if I go 3 halves of a wavelength? Again, perfectly in phase, constructive. So, in this case, it turns out if you start off with speakers that were already phase shifted, if one source is pi shifted from the other, then we got another result here. We've got that, well, actually, I'll just go back to my previous result. It's easier. We can just add a little addendum here. If one speaker is pi phase shifted from the other speaker, and remember, these don't have to be speakers, they could be any wave source. If one speaker is a pi phase shift from the other speaker, well, then you just flip-flop this. Then you just take this rule, and now these give you constructive right here. These would give you constructive, and these up here would give you destructive. And so the whole thing just gives you the opposite result. Now the whole integer wavelengths give you destructive, the half integer wavelengths give you constructive, and I have to impress upon you the idea that this does not just apply for speakers. This applies for light in some sort of double slit experiment, or light in a thin film experiment, or sound with speakers, or water waves. Anytime that's the case, this rule holds. In fact, this is the fundamental rule for almost all wave interference aspects, is that the path length difference, along with whether there's a pi phase shift, a relative pi phase shift between the two, will determine whether you get constructive or destructive interference.